Good afternoon, everyone. Welcome to the SLDS webinar in October. Today, we are pleased to have Professor Runze Li as our webinar speaker. Professor Li is the Eberly Family Chair Professor in Statistics at the Penn State University. He serves as the co-editor of Annals of Statistics from 2013 to 2015, and he's a Fellow of IMS, ASA, and AAAS. His recent honors and award also includes Distinguished Achievement Award of International Chinese Statistical Association, IMS Medallion Lecture in 2023, and IMS Carver Medal in 2024. Professor Li's research interests include theory and methodology in variable selection, feature screening, statistical inference for high-dimensional data, robust statistics, nonparametric and semiparametric regression. His interdisciplinary research aims to promote the better use of statistics in social behavioral research, neuroscience research, and climate studies. Without further ado, let's welcome Professor Li. Professor Li.
Yeah, so first of all, I would like to thank Zhihua for invitation and also thank her for organizing this series webinar. So far, I've been attending several of the webinars, so I'm really enjoying it. So, but also give me a great pleasure to deliver this webinar. Yeah. So today I'm going to talking about high-dimensional statistical inference, which is I have been working on this topic like several years, and so but my presentation mainly was based on Ji Zhang and Xiu Huan, my collaborator work on with Ji Zhang and Xiu Huan Yu. Both of them are my former PhD students. So okay, let me give some introduction on this topic. So when we're talking about inference, I think the first thing is people thinking about testing for normal mean. And so, like if the population is finite dimensional, so for normal mean, so the classical one, the classical test statistic, it will be Hotelian T test or Hotelian T square test, right? And so when people thinking about high dimensional inference, so actually, the high dimensional inference for normal mean problem would go back to 1950s and 1960s paper by Dumpsters. And so in these two papers, basically the authors, talking about how to handle the singularity or sample curve matrix. And as far as I know, like after this paper published, not much work on this topic until 1960s, 1996, not 1960, 1996. So in the 1996, I think there are a couple of papers on this one. The first one I think is Loister. So basically, he proposed exact testers for normal mean by projection based on matrix spherical distribution theory, and also they are in the follow-up work in his 1998 paper. He's talking about more like linear structure, textual linear structure in the linear models. Okay, and so another famous paper in 1996 is by Zidong Bai and his student paper published in Statistical. So in this paper, so basically the author use randometry theory to study the effect of high dimensionality, and found out actually Hotelian T square becomes almost no power when the ratio of dimension to the sample size turn to 1. Okay, so in that setting, basically, so they actually they advocated the L2 norm based testers, and so the bias actually is because based on randometry theory, so actually allowed the population could be beyond normal distributions. Okay, and so after that, so since 1996. So there are many work. Question here, there's someone here. I don't see.
It's Howard.
Howard, okay. Any question?
Let me unmute.
Okay.
Yeah, Howard, please go ahead.
Hello?
Hi, yeah.
Oh,
Question?
sorry. Yes, can you go back to the previous slide, please?
Sure.
So when
Okay.
you say the has no power when the ratio of dimension to sample size is 1, what dimension is this that we're talking about?
This is, for example, the dimension, the sample size is equal to the sample size of data. Here we are talking about testing mean, right? So basically, you have such like dimension is p, sample size is n, and p p over p over n go to 10 to 1. In that case, alternative test actually not have no power.
So this is like the number of
Variable, the number of variable to the number.
yes.
Yeah.
Okay, thank you.
Yeah. Okay. Good.
Yes,
Okay.
thank you, sir.
Yeah. And so since 1996, there are many work actually being published try to improve the bias work. Okay. So here I list some of them here. So essentially, like since like 2008 up to this year, there are many work actually published in this topic. Okay. So it's impossible for me to review all those work, okay, but I just give some reference so people actually you might interested into looking at. Yeah, and here I put them into two non-biased. That's that's very similar to the biased work. And later on, more recently, actually, people find out that two biased norm tester is good for dense signal. Okay, so for sparse signal, it doesn't working very well. So people actually propose infinity norm based test for the test on mean here, and here also there's some work. And of course, like there's something between, right? L2 to L infinity. So people also thinking about adaptive tester. So basically try to decide L2 or L3 or L5. So the data choose it. And so this actually work is designed by Gong Jinxi and his co-author. He published several papers on this topic. And so more recently, people also thinking about the projection tester on that. Okay. So so why we are interested in why I'm talking about the test along the mean here. The whole thing is that there's some direct application of high dimensional mean testers. So so basically is that so many high dimensional hypotheses can convert to the equivalent hypothesis on high dimensional mean. So if you are able to do the high dimensional mean, so basically you might apply it to other settings here. So for example, suppose we have data Q here, and we estimate the high dimensional parameter using under the loss function theta. Okay, and we are interested in testing theta equals theta 0. Let's say that. And so when it's just the idea is very similar to the score test. So we might consider another null hypothesis testing the mean of gradient of the loss function when theta equals theta 0 and that equal to 0. Okay. So under some minor condition, actually we can show that these two hypotheses are equivalent. So you can test either way, right? So the set when testing theta to theta 0, the model could be in very general settings. For example, you might testing linear regression coefficient to be certain to be beta to beta 0, something like that. But this one actually can convert to another equivalent testing on this one. So when you deal with the taking the mean of the gradient of the loss function equal to 0. And so in practice, actually, so the gradient of loss function can be written as a sum of IID along the vectors. So in this case, actually, you already convert the problem, origin problem, testing theta to theta 0 to the testing the mean, the one sample mean problem, right? And so for the you want to testing the subvector theta 1 to theta 1 0, and so basically you can using the correct score on the gradient of loss function and to construct the testing. So later on I'm going to using this trick to construct a tester. So you will see more of later on. Okay. And so now I come back to the state inference for high dimensional regression models. And so this topic actually I think becomes very active research topic since 2014. So last year actually I think there's 3 famous papers was proposed. One is device lasso, and the second one is disparsify lasso here. And so those actually they propose basically how to construct confidence interval for individual regression coefficient, how to construct confidence interval for the individual regression coefficient, or how to testing on the individual regression coefficient for linear model and general linear model. And so the idea I think actually can be also regarded as a kind of like decorated score tester. And so in 2017, Liang and Liu actually also proposed a decorated score tester for the M estimate. So actually that will be for very general setting here, and more work here along this line here. And so also there's some work on we here call it in 2021, there's also another proposal we call recursive online score equation measures. This is also a proposal to deal with to construct confidence interval for low dimensional subvectors of regression coefficients. Okay. And so as I just show you, so basically all those work actually is more focus on construction confidence interval for one or finite dimensional parameters, and they are applicable for testing high dimensional parameters. Basically, you might integrating the FDR or Barnoni correction procedure. So essentially, you are able to construct the testing for one dimensional, and then you using FDR procedure, you can take the high dimensional in that case, right? And so I would say all those work actually, you see it's more focused on finite dimensional parameter settings here. And so today I'm going to talking about linear hypothesis. Okay, and let's consider linear regression model, the model 1. Okay, pretty standard setting. We are going to constant variance here. Okay, and so without loss of generality, let's assume the mean for x equal to 0. And so and we are going to denote the sigma to be common matrix of x, and omega will be the inverse of sigma here. Okay, so we are interested in testing the linear hypothesis in the equation 3. That's been with C transport beta star equal to gamma 0, and C, the matrix C is a pre-specified P by R matrix, and with rank, column full rank R here, or call R to be less than P here. And also here, gamma 0 is also is pre-specified vectors here, right? Okay. So and so there's the linear hypothesis usually give a pretty general formulation for many hypotheses. We are interested in the practice. For example, you might take C equal to the identity matrix with order P. So in this case, we are testing beta star equal to gamma 0. And we are going to refer this one as a global hypothesis testers. And so I did some over here. So basically some over here. So basically in 2018, Xia et al. Actually they proposed in minimum testing based on P component-wise device lasso estimator. Basically it just essentially just for each individual coefficient you construct a device lasso estimate, and then you construct a testing statistic, and then using FDR control that kind of strategy to construct that. Yeah, or you can simply take a maximum and then you divide the limiting distribution on that. And so Go and Chen's paper here, basically they also because global hypothesis, they actually you can convert it into a one sample bin problem, and so in this way actually propose a use statistic method test here. And so more recently, actually, Zhao et al. Actually they deal with this problem by converting this null hypothesis, that's been this beta star to equal to gamma 0 into an equivalent test on the expected value of score vectors. And then they extend the one sample bin test for this one. Okay, so basically is doing this way here. And so another common user case is that you would take C equal to IG0. That's mean essentially you are testing a subvector of beta equal to 0 or equal to gamma 0, something like that. Okay, and so they also some work on this topic too here. Okay, so so all those what you can see that is the pretty much limited. That is the rank of C either to P or low dimensional. When C equal to P, basically that's the global tester. In this case, you don't need to deal with kind of Newton parameters. Okay, because you are testing under null hypothesis, beta star beta equal to beta 0, gamma 0 is wrong, right? Yeah. And so for the second case, basically you R is low dimensional, in particular R equal to 1 or 2. So in this case, the Newton parameter is P minus R dimensional, is high dimensional, but because R is finite, so you are able to control the estimation error of the Newton parameters in this case. Okay, and so in practice, so when you talk about high dimensional, so typically we will refer to P is much bigger than N in this thing, right? And so we might estimate in the linear hypothesis in this way that both R, that's the rank of C, and P minus R are more than N here. That means R and P minus R actually both are kind of bigger than N. It's kind of high dimensional, you can say that way. Okay, and so here's some motivating example here. So for pathway analysis in genetic study, we know the number of genetic markers in the pathway, and the remaining genetic markers can be greater than sample size. Okay, that's mean that you want to testing a particular pathway have effect or no effect. So that means essentially you want to have the R could be bigger than N, and so the remainder ones P minus R also can be bigger than N here. Okay. And we know that nowadays people also talking about AI or large language model. Let me give you an example that could be also used could be useful in a large language model. Right? Okay, suppose we apply the large language model such as ChatGPT for summarized documents. Okay, and so we might need to decide which document to be include or exclude to save cost. I know like when you're using free version, ChatGPT can help you do something, right? But you really want to for the business purpose, you really using when you need to pay it. And so basically, you too many input, that means the document is too big, so you might cost too much money for that. So in this case, so you have to decide what document to include or what document not include, right? So actually, we might formulate this kind of problem as in kind of testing the parameter related to the not included excluded document to be 0 or something like that, right? And so in this case, you see the dimension of feature space corresponding to include document and exclude document could be also greater than the sample size, right? In this case. And so this also could be useful in that situation here. And so this actually motivates us to consider linear hypothesis without requiring rank the rank of C less than the sample size. Okay, that means we are going to allow both parameter or entries, a nuisance parameter to be high dimensional. That means it could be bigger than sample size. Yeah, that's the setting actually we are going to consider here. And so here is my today's agenda. So I'm going to show you a testing procedure, or actually new testing procedure for the null hypothesis, allowing R bigger than N. Okay, I'm going to show some theoretical property for that, or the proposed testing procedures. And later on, I'm going to introduce like implementation friendly versions of the tester. And so I also going to talking about some power enhancement to have more power on the proposed tester. Okay. Okay. Here I'm going to show you how to develop the tester statistic here. So if we denote the PC here is a projection matrix related to C. C is the load for the linear hypothesis, and omega here is the precision matrix of X here. Okay, and so if we define Z and W in this way here, so we can decompose the X transport beta star into this way here in the equation 4. Okay, and the reason I define PC inverse omega is so with this definition actually Z and W are uncorrelated. So essentially that's you do decorrelation in this way. Okay, and that's important here. So so if we do this, like we decompose X transport beta in this way, so essentially you can see we want to testing gamma equal to gamma 0 in this formula, because gamma equal to by doing gamma equal to C transport beta star here, right? So basically but essentially we are transfer this linear hypothesis to be just easy way to deal with that. So gamma equal to gamma 0. And so so you are denote the L gamma to be the, I think, okay, I have to be here to be equal to this respective value of y minus X transport beta square here. And then, so in this case, actually, you will take a gradient of L here and set gamma to be gamma 0. Actually, you can have this equation y here. And so you see that, so in this equation, if Z is not degenerate, that means the second moment of Z is positively. That means this match is positively. You will see that so basically this gradient equals 0 if and only if gamma equals gamma 0. Right? That means if I want to testing gamma equals gamma 0, essentially I can just testing this gradient to be 0, right? And so so basically we convert this one, and so now actually if I define D to be this variable D to be this one here, G times Y minus X transport beta star here, right? And so in this case, essentially we are going testing the linear hypothesis actually equivalent to testing the one sample mean equals 0, right? So this actually that's I already using very simple way. I transfer this the linear hypothesis to be testing mu D equals 0. I think there is a question. Yeah.
Yeah, I saw that. But it disappears shortly.
Could you show up again? Have question here? Could you raise a hand again? Because I have many people I know, so actually difficult to see.
Yeah. I'm not sure if I accidentally clicked the wrong button, but if you have a question, feel free to raise your hand. I was trying to unmute. Yeah, let's keep going.
Okay, keep going. If a question, don't be shy, just ask. Yeah. So essentially here, using the trick, actually, I converted the linear hypothesis to be the one sample beam problem. So of course, if we know the D here, okay. So suppose we have ID sample from population, we can define DI corresponding in this way here, right? And so if I is finite, essentially, if we are observe DI, basically we might apply for fertility test. And so as I mentioned before, you are bigger than sample size. Here, sample size using big capital N here, right? Because later on I'm using small n for other purpose. So so you R is the however we R is bigger than the sample size, or the ratio R over N is close to 1. So actually we know that fertility test actually going to perform badly, okay? And so one way is that, well, we are now going to using fertility test, right? So here actually we want to using the strategy that proposed in Chen and Qin's work here. So essentially we want to define the U statistic here. So basically Tn star. So basically, essentially you can just think that this is the L2 norm of Di subtract the related in that way, right? Okay, and so if we know D, we done, right? Of course, in the practice, we don't know D actually is not observable. So because beta star is unknown, omega is unknown here, right? So so basically you want to using D to construct the testing you want to using the, so basically you want to using the Tn star or the testing hypothesis. Basically, we need to deal with the beta star and omega here. And both of them are high dimensional parameters here. And so the challenging is that, so, well, in very intuitive, you'll say, okay, let's substitute the consistent estimator, right, into Tn star. But it doesn't work. The whole thing is R is also go to infinity. If R is finite, it might work. Okay, if R equal to 1 or 2, it might work, right? That's also the people actually working on. But when R is big, so basically, so that's the error accumulation over the high dimension actually doesn't work, right? So one way when this thing doesn't work, so way in two ways, like okay, that's simple, right? Let's do data splitting. Okay, so with data splitting, that means that, well, we randomly partition data into 2 parts, okay, equally sample size, okay, you know, right? And so that's the reason actually I using capital N for sample size, and that's her simplicity. Let's assume capital N equal to twice or small n, okay, n is basically half of sample, right? And so then we using Q1 using half data to estimate unknown parameter, beta star and omega, and using Q2 to construct the testing statistic. Okay, so I denote by Tn. So in this way, so basically, well, it seems to work, right? So basically, it seems at least we are able to implement it. So in our numerical study, actually, we're using lasso to estimate beta star and the lasso not-wide regression to estimate omega. So basically, you can apply the regularized method to estimate beta star and omega here. So the whole thing here is that what we need is just the rate, the convergence rate of the high dimensional parameters estimated here. Right? So basically, you might using other regularizer also work here, but simply here we just using lasso and lasso not-wide regression because there are many iterated results on those estimators, so you might direct using them. Okay, and so here so let me so certainly so under some conditions, call the condition might be strong condition. Okay, some condition. So we able to establish the asymptotic normality or Tn here. So basically, its asymptotic mean will be sigma this one here, H transpose sigma z square H here, and H will be the difference between gamma 0 here. Okay. And so we also have the asymptotic variance on this one here too, right? And so here, the trace of sigma h squared usually go to infinity. So what we need is just the ratio consistent estimator of this quantity. So you don't need to consider estimator, but you need the ratio consistent estimator of that. Okay, that's kind of little tricky here. Okay, so now actually we can using Tn doing the testing hypothesis here, right? But there are two limitations here. Now, one thing is because in the construction of Tn, so we need to estimate omega here. Omega is basically P by P matrix, right? And so estimation of omega could be quite expensive in this case, right? The second one is that we using data splitting, and we know that data splitting by result in the lower power because you essentially using half data to construct the taking statistics, right? Okay, so so in practice, right? So in practice, the first thing is that actually it's challenging in obtaining the consistent estimator of omega, right? That's right, because you don't have extra assumption on covariance. Okay. The second one is substituting the omega hat can also cause additional estimation error in our test. Okay. One way here, so in practice implementation, one way is that, well, can we do we need to estimate omega, or we don't need it, right? So one way is that you just replace omega by a pre-specified positive matrix. So we just say that's working matrix here. And so this idea is like very similar to the people. So the general estimating equation. So in that context, people have like using the working correlation matrix to replace the true correlation matrix here. But the idea is pretty similar. But later on, actually, you'll see we using omega essentially just because we want to G and W are uncorrelated. So that decomposition actually is kind of decorrelation or automatic decorrelation. So so in this context, actually, you using IM actually might be okay. Okay, something might be okay. So that's one thing, right? So okay, so let's say okay, I don't want to estimate omega, so I just simply say okay, I just want to replace omega by, for example, identity matrix. Okay, and so you do that way. So we actually we still can using data splitting strategy to estimate beta star. Okay, and so the resulting estimate we want to denote to be the result estimate to be the TNM here because depend on M, right? And so we find actually we find out we do some numerical comparison. So we find out the choice of M actually is not sensitive in our numerical study. Okay, and the second one is like even we take simply M to be identity matrix. Okay, so you M to identity matrix, we find out TNM and TN actually have comparable performance. So this one actually could be help us a lot. So basically, essentially, so in practice, actually, you don't have to worry about estimation of omega. Yeah, that's one thing, right? And also, we also can establish the asymptotic normality of TNM here. So essentially, the form is pretty similar. So basically, but you want to involve this complicated here M here, but they also sigma also is here in here, right? Yeah, the sigma in the sigma M here. Okay. So with this asymptotic, under the null hypothesis, H will be equal to 0. So basically, we can using this one actually for testing hypothesis, or the testing the hypothesis. But well, still not good enough because like we just handle try to avoid the estimation of omega. So we still connect power loss because data splitting, right? Because we still using the data splitting to estimate beta star here, right? So next step actually, so we are thinking about how to enhance the power of the TN or TNM here, right? So when you're talking about power enhancement, basically there are three general principles to follow. Okay. The first one is that after you do power enhancement, the resulting test signal size distortion. Okay, so that's basically you want to retain the correct type 1 error rate here, right? And the second one is the power enhancement testers should be at least as powerful as the original one, right? That makes sense, right? Otherwise, so you have some gain, have some loss, right? That's not called enhancement. Right? The third one is that the power enhancement tester will be substantially enhanced over a more general alternative. So basically, that's been you can using it in general way here, right? So here, I'm going to consider two types of power enhancement. The first one is that to deal with data splitting. Okay, because we know the data splitting actually will lead to power loss, just because we don't utilize all information in the data, right? And so to deal with that, so one natural idea is to utilize the sample information by swap the law of the two subsample Q1 and Q2. So originally we using Q1 to estimate the Newton parameter, and using Q2 to construct the test sensitivity, right? And so well you can switch them, right, the law, right? So but we might using Q2 to estimate the Newton parameter and then using Q1 to construct the sensitivity. So this by one the law of two subsample, actually we can get a two set of output, right? And so we in general we know that TN1 and TN2 are going to be correct, in general correct, but so it ended up under some condition. Actually, we can show that these two actually behave like asymptotic independence. So that's when you end up them these two together. Actually, they will turn to normal 0, 2. Okay. And so in this case, so because we have normality, all right, so actually we can define a power enhancement test statistic in this way. Basically, you add up together and divide by standard deviation, all right? And so using this one, we can construct we will reject our hypothesis under this situation here, right? And so first thing, like you will see by this construction, you will see certainly this test will retain the type 1 error rate. Okay, so that's been we can retain type 1 error rate. Okay, the second one is the application. This strategy actually is very similar to the cost refit. The cost refit, the idea is that was originally proposed for the error estimation in 2012 paper by Fan, Go, and Hao here. Okay, so we also are able to show that this test statistic actually is more powerful than the original one. Okay, than TN. But well, you say, well, it seems like using all data is as powerful as the Tn star? And the answer is no. Actually, data splitting also lost information basically. Okay, so that's the for sure. So I want to just like make it clear here now. Okay, the second one is that we want to boosting power under different alternative space. Okay, and so the so we know that the Tn or the power enhancement one, they essentially is L2 norm-based tester. And we know the L2 norm-based tester actually are powerful for detecting dense signal, but less powerful to detect sparse signal. Okay, on the other hand, infinite norm-based tester are powerful at detecting sparse signal and less powerful to detect the dense signal here. Okay, and so now actually we are going to boosting the power under the sparse alternative. I think that's the idea. Right, so in this case, because essentially we want to consolidate, the infinite norm test, in this case, right? So in this case, actually we formulate the null hypothesis, linear hypothesis into individual one-dimensional linear hypothesis. Basically, you just take it one by one, right? And so okay, basically, right? And so now actually we want to construct a testing for this one here, right? And this one, CK, the rank of CK is just 1 in this case, right? Okay, so very intuitively, we can extend the construction, the ideal construction TNM applied to the H0K here, right? We call CK to 1. So but the idea is that because the rank of CK equal to 1. So in this case, there's some bias becomes negligible here. The original you deal with CK transport beta actually when R go to infinity. So the variance of C transport beta hat actually might be the variance also go to infinity. Okay, because R go to infinity in this case. So in that case you might allow some bias. But when you consider when the rank equal to 1, actually the bias is you see there, right? So in this case, we need to do something, all right? So essentially, we need to using the bias or the decorration skill in this case. So very specifically, let's only consider M equal to identity matrix here and define PK is just the projection matrix or CK here. And so we can define ZK will be this way, and gamma K and WK will be just like UK here. And essentially, we want to decompose F transport beta to be in this form here. Okay, and so this decomposition is just like as I talked before. But the problem here is that I just mentioned that M equal to omega, so we know the G1 and omega W tilde they are no longer uncorrelated, and that makes things trouble here. So essentially, we are going to using decorrelation version. So basically, we want to decorrelate it in this way here, using decorrelate version, and then using this one, basically, you can show that under null hypothesis, the expected value of this expected value actually equal to 0 for all k. So again, using this one, so essentially you define dk1 to be this one, and then convert this null hypothesis to be testing the expected value of dk1 equal to 0. That's the idea, right? And so in this case, basically the idea I just talking about still apply here, applicable here, basically using data splitting. So you can estimate theta K and beta star using regression methods. And so essentially, so we are able to construct the X and K here statistic here. And so we can be sure that this statistic actually could be asymptotically follow the normal 0, 1. So in that sense, actually, we can define the power enhancement component in this way here. Okay, And this one actually is the it's just like when you deal with sparse statistics, basically you using threshold to threshold out the weak signal, basically, right? And so so in this so after you're doing that, so basically you can so for a testing statistic, so T here could be either Tn or Tn star, and so basically you take absolute value of this origin T statistic and plus the power enhancement term here. So you get a new one here. So I did not using x stand for single here, right? So basically it's one power enhancement testing here. Okay. And so okay, let me start here. Yeah, so basically we can show that. So you using so you using this one for the testing. So actually you can show this the resulting extreme will retain the type of error rate, and we have more powerful, will be more power under alternate hypothesis, something like that. Okay, and so because of time, so I want to skip quickly start here. Another construction here for power enhancement. So you know, like so I just talking about, well, we convert this one into the individual testing. It's okay here, right? So alternative, actually, we can also, because we know that we actually convert this one to an equivalent test null hypothesis mu d equals 0, right? So if we think of mu d is sparse, so we might want to testing individual mu d component equal to 0. Okay, here. So in this case, we can also, pretty similar, we can also construct a power enhancement test, the components. So essentially, the idea is very similar to the one we have, but essentially, what you need is that you just need to do the consider decoration version here in this way, and then you can convert the testing null hypothesis equivalent to testing the mu k2 equal 0. Mu k2 will be, basically will be equal to the expected value of dk2 here, and dk is just the case component of this one here. Okay. Because of time, so I'm going to skip all those things here. So in this case, actually, we can also very similar. We can define the power enhancement term here, right? Okay, and so that's corresponding to this statistic here. And so even more interesting thing is that, so you know, like when you're talking about when we're testing L0K, that's been the some individual one. This one is just one dimensional, essentially one dimensional parameter here, right? So in this case, indeed we don't need to do the sample splitting, right? We don't need sample splitting because this is the just one kind of low-dimensional parameter you want to testing on that. And so it ends up actually we might using we might have another versions that we might estimate theta k or beta star using the whole sample, and then construct the testing statistic using the whole sample. This actually comes back to another power enhancement test term here that using JD 2PE here. So here is like basically it's using capital N just stand for like using all sample for this one. And so because this one is using all sample, so naturally we also can using the power enhancement for the data splitting one. So we put in here, so you get another boosting here. Right, and so very similar for the DK2, you can also do very similar in this way here. Right, yeah. Right. Okay. And so let me give using some time to show you some numerical result here. Okay, so we generate data from linear regression model. Okay, and so this way, very typical setting, you have standard error. The error will follow standard normal distribution, and X will follow the normal distribution here, right? And so my presentation actually going to focus on NP equal to 200 and 600 here. So I'm going to only show you 3 scenarios. Okay, so the first one is the global testing is you want to take the beta star equal to 0 or not. Okay, yeah. Too high question?
There's a question from the audience, sorry.
Okay.
Yeah, so from Zelin, so I'm interested in this cross-refitting idea and have a related question. Is there a fundamental upper bound on how much power we can obtain from such a cross-fitting strategy? And can the power asymptotically approach the baseline without sample splitting?
Well, let me go through I know we have some time for the question, right? So let me answer this question well, after I go present the numerical result. Okay. Yeah.
Okay.
Okay. Yeah.
Sure.
So that will show you something on that. Yeah. Okay. So the second scenario is just like, R equal to basically R equal to half P here, something like that. So it is 300 here. And so alternative hypothesis will be some small data, there's some 5 along 0 here. And the third scenario actually will be just like, will be this linear hypothesis, but we add up 2 more linear hypotheses in compared to N2 here, right? And we have more simulation result in my paper. So so like here. Okay. So this one, so basically this table actually try to show you 2 things. One thing is the working matrix in you will see omega hat or identity matrix. Okay, want to compare that. The second one is that we want to compare. You do the sample splitting just using half data to construct the testing statistic, or you using cost refit strategy to get information back here. So first of all, we will see here there's some using this table here. So one thing you can see all the testing statistic in all cases, right? They retain type 1 error rate quite well. Okay. And the second one is you will see omega hat, you take the working matrix omega hat or identity matrix, in terms the performance very comparable. Okay, you will see you just compare single to single here, right? Or double to double here, you will see very similar. So essentially that's in practice you might simply take M equal to identity matrix. Okay. And so you'll see the table also show you the cost refit actually can have much more power than you just do, you throw half data here. And I think the third question is, well, how much loss you using the cost refit? And so the idea actually is really hard to quantify it, but theoretically, actually, we can show in our paper. Actually, we can show the power for the, if we know the beta, pretend we know we can estimate beta star and omega perfectly well. Okay, and so in that case, in the paper we do have that one. But you want to derive the upper bound and lower bound, I think it depends on alternative actually in terms of power. There's no uniform bound for that. Yeah. Okay. This table basically show you that. And so here I already talking about remark here. And so so this table actually show you some numerical comparison for the power enhancement here. And so basically I have 4 power enhancement testing statistic here. So basically we have D1, D2, and we have the 2 different scenarios to construction the power enhancement here. And so I also including some other existing testing, Ma et al. 2021 and Go et al. 2021 testing, because these 2 tests actually is applicable for scenario 1 and scenario 2 here. And you will see that, so basically, you using double HT basically is that the basically is that is double is that you using the cost refit strategy to construct the statistic, and then you add up the power enhancement term there, right? And so this way actually you will see overall this one actually in this table actually you will see This statistic actually do quite well in this case. It can if it beat all of them right here, right? Yeah. And so, well, you might wonder, so it's always true in this case. So the whole thing is that you compare TX one or TX2 here. So they are similar. No, okay, yeah, TX1, TX2. Yeah, they're similar, right? And TD1 and TD2, they're similar. So somehow it's hard to say you compare this one, TD1 and TD2 here. It's really hard to say which one is better actually. So we are in our paper, we also give some example actually. TD1 PE might be performed better than TD1 PE2 here. Okay, yeah. Okay. I think I have some remark. Basic remark here is by show you the power enhancement actually just the work as we expected in simple way to say that. So we also apply the teaching statistic, the teaching procedure to a real data example. So basically, this data actually is come from the it's a genetic study related to breast cancer. Okay, data here, and the sample size 156. Okay, and Y actually is the expression measurement of gene right? Or this one here, associate BRCA1 here. I think this stands for breast cancer, something like that. Yeah. So here we are interested in those to identify other gene which is highly associated with this gene. Basically, that's the idea. So in this one, in this data set, actually they also provides different gene ontology molecule functions. Basically, it's pathway. Okay, so here there are many pathway, but here we are consider 125 pathway, and so each pathway actually they have like more than 150 and up to like 2096 pounds. Okay, so the dimension could be certainly could be higher than 156 here. Okay, so here basically we just thinking about like kind of, well, for each goal ID we just consider a linear regression model, and we want to testing a global test beta k equals 0 or not. Okay, and so because we are simultaneously consider 125, so we also might consider apply harmonic correction in this so in identifying significant genes ontology group. Okay, so so as I mentioned, okay, so the null hypothesis beta k equals 0 is a global hypothesis, especially you're taking the entire coefficient in the regression model is 0 or not, right? So so how the global so basically it is no Newton parameter to estimate. So in this estimation it's very simple. So it is we don't need to do the data splitting. Okay, we don't need to estimate the Newton parameters. So so in that actually we only can using the Tn and with identimetry here, M equal identimetry, with an enhanced the second enhanced term here for the null hypothesis. And so because it's the global test actually Zhong and Chen's testing can be also applied for this setting, so we including our comparison here. And so here is that we have this is the result. This is the result of our tester, and this one is for Zhong and Chen's tester here. And so this column stands for we solve harmonic correction method will identify 17 group to be significant, and Zhong and Chen will be identify 14 be significant. So with harmonic correction, so basically we will identify 6, and so Zhong and Chen will be identified non-significant. So you just compare these ones. So simply you can say for the significant one, so basically our p-value will be much smaller than Zhong and Chen's one. Right? Otherwise, they would not pick up in this way. So in that sense, also implies that our testing might be more powerful or powerful than the Zhong and Chen's method. Yeah. Okay. So here's some concluding remark. So basically, I introduced some new teaching procedure for linear hypothesis. And so that was kind of the major challenging is how to deal with the high dimensional Newton parameters when R is diverging in this case. The technical challenging is this one. So we try to deal that with using data splitting and then using power enhancement to bring some power back, something like that. And I think that's all my talk. Thank you very much for your time. So I'm here for question here now. Yeah.
Thank you very much, Professor Li. Let's move to the Q&A session.